Okay, so maybe I'll slowly start with a few remarks from the internet, and then I'm going to use the blackboard again. So the last lecture of this series is about tropical discriminants, and it's going to be an introduction to this material in a paper with Alicia Dickenstein and Eva Feichtner. So the first sentence of the abstract says, tropical geometry is used to develop a new approach to the theory of discriminants and resultants in the sense of Gelfand, Kapranos, and Zelevinsky. And this leads to formulas. So I'll explain what this is about. So who are Gelfand, Kapranos, Zelevinsky? Well, Kapranos, you already heard, the Kapranos rank. So here they are. So this is the book. So I'm going to call that the GKZ book. I'm going to make a reference to this. So this is a very well-known book from the early 90s called Discriminants, Resultants, and Multidimensional Determinants. And I'm going to call that the GKZ book or the green book. And you look at this, you know. So it's a very nice book, has lots of useful stuff. And the main focus is so-called discriminants, A resultants and A discriminants, triangulations. And I'm going to give a new approach. I'm going to describe a new approach to the material in this book. But before we do that, can't resist the temptation. So it's really quite unfortunate that we're having this conflict, right? The Georgia Bankard is just giving a wonderful talk over there on the other side on the Women's Mathematics Conference. And I was just able to peek in for a few minutes. A few of us peeked in. And Georgia pointed out that undergraduate students sometimes, can do wonderful research and make important contributions to mathematics. Now, this book grew out of work with graduate students. So here's some stuff that we wrote, including tropical geometry. But then most of the other material down here is written by graduate students. This is sort of material at the interface of algebra, statistics, and biology. And I couldn't resist the temptation because sometimes, smart undergraduates become smart graduate students. So the same Eric Kuhl that was mentioned by Georgia Bankard became, as a graduate student, got involved. He became a computer science student. He got his PhD with Lior Pachter, who was my collaborator on this project. Same guy, yeah, it's identical person. So he did this other thing over there as an undergraduate, and then as a graduate student, he did this and worked on the geometry of Markov chains. Anyway, so I just couldn't resist. So everything is related, Same. He graduated. Actually, he had a postdoc. He left academia. He works for a software company. So he works for a company now. But he was a very smart guy. And so you see some of the, Michael Joswik is there and some other people. And in any case, so this was a fun project. Okay, so let's close this and talk about discriminants. Okay. So the way we're going to set this up is we're going to fix an integer matrix. So A is an integer D by N matrix. And I'm going to assume that the rows are linearly independent. And I'm also going to assume that the all-one vector is in the row space of A. So this is a technical assumption, So it's a D by N matrix of maximal row rank containing the all ones vector in the row space. So this matrix defines a family of Laurent polynomials. Laurent polynomials having n terms in D variables. Namely, the family is, so the variables I'm going to call T t1 up to td. And this has n terms, so it's the sum j from 1 up to n. I'm going to call xij. I'm going to call the coefficient of the x for the jth term xj. And then the monomial is going to be is simply the monomial specified by the columns of the matrix. So it's t1 to the a1j, t2 to the a2j, up to td, up to adj. So I have a d by n matrix. Each column gives me a monomial, a Laurent monomial in d variables. And then I take a linear combination of those n Laurent monomials with unknown indeterminate coefficients xj. And the question is the following. Under what conditions on these coefficients? So under what condition on the coefficients x1, x2, up to xn does the hypersurface defined by this polynomial does the hypersurface defined by this polynomial have a singularity? And since these are Laurent polynomials, we have to ask this question, for zeros in the algebraic torus, C star to the D. Okay? So for any choice of the x's, if the x's are some particular numbers, I'm going to get a hypersurface. It turns out that if I pick random x's, this will be a smooth hypersurface. But for some special values of the x's, this hypersurface might have a singularity, and I'm going to be interested in characterizing exactly when this happens. That's going to be the goal of this talk. Okay, so let's use this as a definition. So we're going to define the A discriminant. So A is this matrix. So the A discriminant, which I'll denote by a delta sub A, is the closure of the following set, of the set of all points x in projective n-1 space. So there exists a T in C star to the D that is a singular point on this hypersurface. So f of t equals the derivative with respect to t1 is 0 all the way df dtd is 0. Okay? So I write down this system of d plus 1 Laurent polynomial equations in d variables. So I require that f vanishes and all of its partial derivatives vanish. And I'm interested under what condition is there such a singular point t on the hypersurface. Now, if x is random, then this will have no solution. So for random x, this will be a system, an overconstrained system of one more equation of unknowns. But for some special x's, there might be a solution. The closure here, it turns out you can take either the Zariski closure or the analytic closure. They will give you the same answer. So you can take closure in whatever sense, and you will get the same answer. Now, this is a variety. This is a variety. And often but not always, it's a hypersurface. Okay, we're going to be interested, when is it a hypersurface? Usually it's a hypersurface, but sometimes it isn't. And if it's a hypercurved surface, so in which case we're going to identify this hypersurface with its defining polynomial. Is identified, with its defining unique up to sign irreducible polynomial. And we're going to make this polynomial is the irreducible polynomial with integer coefficients, x1 up to xn. Okay? So in general, for any a, this is an irreducible variety defined over the rational numbers, right? I mean, all the coefficients are +1, right? So it's defined over the rational numbers. In fact, we could define it over spec z, but let's not get carried away. So it's defined over the rational numbers. And if it so happens, if it is a hypersurface, then it's the zero set of a unique irreducible polynomial of content 1. Right? And this polynomial is unique up to sign. Right? So that's a unique up to sign. I'm going to call that the A discriminant also. Right? So if it's a hypersurface, I'm going to just refer to the A discriminant as the unique polynomial. If it's not a hypersurface, well, I'm going to refer to the variety. Okay? Anyway, so the basic reference is this book by Gelfand, Kapranos, and Zelevinsky. This green book is all about this polynomial. That's what the book is about. The book is about understanding this situation. So let me give you some examples. So most of this talk, this last lecture, is examples. So I'm going to give you a sequence of 8 examples, okay? From very easy to more difficult. The first very easy example, let's take d equals 2, n equals 3. Let's take A to be this matrix. 2, 1, 0, 0, 1, 2. Okay? So in my examples, there's always going to be a picture. Maybe I'll do my pictures in yellow. So the picture is simply, so I'm going to draw the matrix A, and the picture is simply, I'm going to plot the columns of this matrix, right? So the columns of this matrix are 3 points on a line, 3 equidistant points on a line. So this yellow picture represents this matrix. And then the polynomial, the family of polynomials, is simply a binary quadrix. Okay, so x1 is the coefficient, t1 squared, x2, t1, t2, up to x3, x2 squared. Okay, and that's the polynomial. And then the discriminant, in this case, is a hypersurface. And this is now really, really, really high school material, right? That's the thing under the square root in the formula. So that's x2 squared minus 4 x1 x3. Well, that's the discriminant. Okay? So this is, what's the situation, right? So what's the hypersurface defined by F in projective space, right? So this is on the projective line, right? This is in projective n minus, I guess it's d minus 1 space, sorry. So d minus 1 is 1. So, for general coefficients, this defines 2 points on the line, right? 2 points on the line. But, if the 2 points come together, then that's a singularity. So there's a singularity when the 2 points come together. And the equation for this to happen, you really learned in high school, right? That means that there's a double root. And that happens when the discriminant vanishes. X squared to the 4th minus 4x1, x3. Oh, this is n. I'm sorry. Yeah, I'm sorry. This is n. Okay. Yeah, sorry. We can make this project. Yeah, you're right. This is n, and there, it doesn't matter here. Okay. So the way I set it up, it's correct. Okay. So that's the discriminant. Now, if you believe, if you were to believe that algebraic geometry is a part of physics, then these 2 points, that's a Calabi-Yau zerofold. Okay? That's a Calabi-Yau zerofold, and that's a one-dimensional reflexive polytope. But Okay, let's go to the next example, 2. Let's go 1 degree up. So let's take d equals 2, n equals 4. So A is now the matrix 3, 2, 1, 0, 0, 1, 2, 3. So now we're going to get the discriminant of a binary cubic polynomial in one variable. And the discriminant is the following irreducible polynomial. This is unique up to sign. So it's 27 x1 squared x4 squared minus 18 x1 x2 x3 x4 plus 4 x1 x3 squared plus 4 x1 cubed. I'm sorry, this is a cubed. It's homogeneous of degree 4. X4, it's x2 cubed, x4 minus x2 squared, x3 squared. So this discriminant has 5 terms in 4 variables. Let's draw the Newton Polytope, right? So this is has a 2-dimensional homogeneity. So let me actually draw the Newton Polytope. That's one of the main points of the Gelfand-Kapranos-Zelevinski book is to draw, to calculate the Newton Polytope of the discriminant. And in this case, the Newton Polytope looks like this, right? So we have, I'm going to give you the coordinates. So this is the point 0, 2, 2, 0. I'm drawing the plane picture by projecting onto the first and last coordinate. So this is 1, 0, 3, 0. This in the middle is the all 1 vector. Here we have 0, 3, 0, 1. And then over here we have 2, 0, 0, 2. Okay, so those are the 5 points. You take the convex hull, and then that's the convex hull. So that's the Newton Polytope. So in this example, the tropical discriminant is, well, it's simply the inner normal fan of the Newton Polytope, right? So the tropical discriminant will look like this. Something like this. Okay? So the tropical discriminant. So if you type this into GFAN, you get this kind of picture back. That's the tropical discriminant. Okay, so that's another very easy situation. Let's do one more example. So in the book, the title of the Gelfand-Kapranos-Zelevinski book is Multidimensional Discriminants, Resultants, and Determinants. So here's a resultant example. So let's take D to be 3, N to be 6, and let's take A to be this matrix. So I'm going to take 0, 1, 2, 1, 1, 1, 0, 0, 0, and then I'm going to take 1, I'm going to take 0, 1, 2, 0, 0, 0, 1, 1, 1. Okay, so let's take this matrix. So, well, this matrix A, the corresponding yellow picture, so now as D is 3, so it's no longer the yellow polytope is not, the yellow polytope will always be D minus 1 dimensional. So the yellow polytope is the convex hull of the columns, so it's has dimension D minus 1. So in this case, it looks like this. Right? So if you plot the 6 column vectors, you get this picture. And the discriminant in this case is the following polynomial of degree 4, 0, x1, x2, x3. This is the so-called Sylvester determinant, Sylvester resultant. Sylvester resultant. x1, x2, x3, 0, 0, x4, x5, x6, x4, x5, x6, 0. Okay? So what is this resultant? Well, that's the equation you get by eliminating a variable from two binary quadrics. So here this is a polynomial, represents a polynomial of degree 2 in one variable. Now you have two polynomials. You have one quadratic polynomial, you have another quadratic polynomial, and this is the unique polynomial in terms of the coefficients that says when they have a common root, right? You all know that from Coxwell-O'Shea, right? Back in your undergraduate days, you all read Coxwell-O'Shea. So this is the resultant of two polynomials of degree 2 in one variable. And of course, you could do the following, right? So high school students in Korea remember the quadratic formula, right? You could solve the first quadric, and plug it into the second, and then get rid of the square roots, and then you get this polynomial of degree 4. So it's the resultant of two quadratic equations in one variable, the Sylvester result. So this shows really that resultants and discriminants, they're like a chicken and the egg, right? So resultant is a special case of a discriminant, and the discriminant is a special case of a resultant. So they're really two, they're very closely related. Mm-hmm. Pardon me? Uh-huh. Oh, delta A is the hypersurface. So delta A is the quartic hypersurface in P5 given by the vanishing on this polynomial. Yes. So delta A is the closure of this set. If it's a hypersurface, I'm going to identify it with this polynomial. Yes, exactly. So delta A as a hypersurface is the zero set of this polynomial. It's the hypersurface of solvable systems of two equations, quadratic equations in one variable. Okay. I said I had 8 examples, so let's make this a little bit more interesting. Okay, here's our old friend, the discriminant. So D equals 3, N equals 6. So this is the discriminant of a quadric, a ternary quadric. So now A, in this example, is 2, 1, 1, 0, 0, 0. So I simply take the columns to be all quadratic monomials in 3 variables. 2, 0, 0, 1, 1, 0, 1, 0, 1, 0, 2, 0, and so on. So that's the A. Corresponding picture, if we plot the columns, we get this picture. I guess I should label these things. So here the labeling is 1, 2, 3, 4, 5, 6. Okay, so then it corresponds to this labeling. And here the labeling is 1, 2, 3, 4, 5, 6. Plot these columns. And in this case, delta A is equal to a half, Well, one usually divides this by a half, so it's actually characteristic free, So, and what you do is 2, x1, x2, x4, and then x2, x4, 2, x3, x5, x5, and 2, x6. Okay, so turns out you need this factor of 2 to be consistent with this definition. So that's our old friend. So that's the determinant of a symmetric matrix, which is the discriminant of a ternary quadric. So that's a very, very old friend, right? And the Newton Polytope is the bipyramid, painfully derived yesterday. And the tropical variety is this picture. And then we calculated our very first Gromov-Witten invariant this morning, which was 3. We intersected this hypersurface with a straight line to get the 3 pictures that I had at the very beginning this morning. Okay, so that's the discriminant. Okay, so let's have a slightly more interesting example. So the next example is 1 dimension higher. That's example 5. Let's take d equals 4. So the yellow picture will be 1 dimension higher. So this will be a 3-dimensional picture. And this is n equals 6. And it's going to be the following matrix. 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1. Okay, so that's this matrix. Now, this matrix represents the vertices. So a shorthand for this matrix, this is really, you know, again, the Toblerone. It's the columns, they form a triangular prism. Okay? So the corresponding yellow picture, you know, is a triangular prism like this. So this is now the discriminant for a triangular prism. It's 1, 2, 3, 4, 5, 6. And so here's the first example where the discriminant is not a hypersurface. So in this example, delta A is a codimension 2 variety. So it's the codimension 2 variety consisting of 2 by 3 matrices, consisting of matrices x1, x2, x3, x4, x5, x6 of rank at most 1. Okay? So these are singular, 2 by 3 matrices of rank 1. So this is so here's a discriminant that's not a hypersurface. It's an example of a discriminant that's not a hypersurface. Okay, so that can happen. Okay, and now 3 more examples. Are there any questions so far? So these are just examples, you know. I'm just making up matrices A. For every integer matrix A, there's going to be a discriminant. And there's no hypothesis except I'm going to assume that the rows are linearly independent and they have the all 1 vector in their span. It's just a technical assumption. Okay, example 6. It's another 3-dimensional example. So now D is 4 and N is 8. So I'm not going to write the matrix explicitly anymore. I'm just going to tell you the yellow picture. I'm just going to tell you what's the matrix. So in this case, A is delta 1 times delta 1 times delta 1, which is the 3-dimensional cube. Okay, so I take the 4 by 8 matrix, whose columns are the homogeneous coordinates for the 6 vertices of the 3-dimensional cube. Okay, so that's the 3 cube. So in this example, it's a very nice example. So delta A is the 2 by 2 by 2 hyperdeterminant. And the physicists call this the tangle. Right? So this is the a tangle because it's an entanglement measure in quantum information. So this is a very nice polynomial of degree 4. And it measures, when a trilinear form, it's the condition for a trilinear form to have a singularity. So it's the determinant, the hyperdeterminant of a 2 by 2 by 2 matrix. a 3-qubit system, right? So it's the discriminant of a 3-qubit system. Okay, 7. So these are all pretty easy. These are pretty small discriminants. Let's get slightly larger ones. So let's take d equals 3 and n equals 10. And again, that's a picture in the plane. And that's the picture, that's the family of elliptic curves. So these are plane cubic curves. So A is the 3 by 10 matrix whose columns form this polytope, again reflexive polytope. And this is the family of cubic curves. So F, and this example is the general ternary cubic in T1, T2, T3. And that's an elliptic curve. So for me, the general plane elliptic curve has 10 coefficients. I'm going to keep all 10 coefficients, x1, x2, up to x10, as independent coefficients. I really, really, really dislike the Weierstrass normal form. Okay? When I say discriminants, J invariants, I keep all 10 coefficients as indeterminants, because that shows us the full combinatorial symmetry. Okay? So I really, really, really would not put a cubic polynomial into Weierstrass normal form. Never would I do that. Okay? So F is the general ternary cubic. So delta A, the discriminant, is a polynomial of degree 12 in those 10 coefficients in x1, x2, up to x10. And now that's a little bit more interesting polynomial. This polynomial has degree 12. It has about 3,000 terms. And singular, it's a small polynomial. It has only 3,000 terms. And I gave you singular code, right? So I showed you the singular code. You just type in 6 lines in singular, and boom, it comes back in no time. It's pretty small, has only 3,000 terms. The Newton Polytope of this, so I guess that's in red, right? So the Newton Polytope of this discriminant, so is a 7-dimensional polytope. It's a 7-dimensional polytope. And the F factor, let me give you the F factor. It's kind of interesting. So it has out of 133 vertices, so out of the 3,000 terms, 133 are vertices, has 513 edges, and so on. 846 two-dimensional faces, 764, 402, 126, and the last one is 18. Okay? So this is kind of interesting. So what happens with these Newton polytopes of discriminants? These are closer to simple polytopes. They tend to have fewer facets than vertices. So we learned, I guess in the second lecture, no, the third lecture, that any polytope by the Weil-Minkowski theorem either has a vertex representation, so you can take this polytope, you can either write it as the convex hull of 133 vertices, right? Or you can write it as system of solutions to 18 linear inequalities. So it's more efficient, actually, to represent it by its linear inequalities. So generally what happens, this is a fairly small 7-dimensional polytope. Happens to be more efficient, though, to write down the inequalities that characterize this polytope. And that kind of makes sense, right? Because when we run this in G-fan, right, so the corresponding tropical discriminant will be a pointed fan with 18 rays, 126 two-dimensional cones, yada, 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 yada. Okay? And the homology, Euler characteristic 132. Right? So that's pretty straightforward. So that's a very nice tropical discriminant. So Now let's do a real example. So here's an example for real men, that is to say, real women. 8. D equals 5, n equals 16. Okay, so now let's take A to be the 4-dimensional cube. So let's do the same thing. Let's go back to the tangle, and let's look at the 4-dimensional cube. So now, this is the hyperdeterminant of a 2 by 2 by 2 by 2 matrix. That's a hyperdeterminant of the 2 by 2 by 2 by 2 tensor. So now it's not a, so here this measures the singularities of a trilinear form. Now this is a multilinear form with 4 factors. And so this tensor has coordinates, x, I, j, k maybe. And that's a polynomial of degree 24. Okay. And so this is the basic entanglement measure for a 4-qubit system, 2 by 2 by 2 by 2 table. And so this is now a slightly more interesting example. It has 2,894,276 terms, and it's Newton Polytope. Newton Polytope is 11-dimensional. And it has relatively few vertices. It only has, 25,448 vertices. And this is an example we calculated once, And so this is still a manageable polytope. So I'd like to argue, a polynomial is sort of manageable if the number of terms is less than the US federal deficit measured in dollars, which is $1 trillion. Okay, this is a very small polynomial compared to the federal deficit measured in dollars. Okay, so that's a reasonably small polynomial. But this actually already required, writing a research paper. So there is a paper by Peter Huggins, myself, Josephine Yu, and Debbie Euster. And what got us into this, actually Gelfand asked this question. So Gelfand in his Rutgers seminar said, so there was a formula for this, but it was a sort of a nested formula due to Schläfli from in 1850, Schläfli gave a nested formula for this. And Gelfand raised it as a challenge problem. Can you actually expand this formula, right? So people tried, right? They went to Maple and Mathematica, and you can't do it, right? So you have to actually work on it and understand the structure, and so we did this. So we had some software that calculated this, and maybe a word about experimental math and computational pure mathematics. I mean, so we had some math idea, we coded this, and then we calculated these terms, these 3 million terms, and the code ran a day. Okay. Now analyzing the output took 3 months. Okay? So this is usually what happens. So in a serious project in experimental math, it's not the running time of the code that's the bottleneck. If you set up the experiment right, the running time is manageable. It will be half a day, it will be a day. The real effort is analyzing the output, just like in biology. Right? So analyzing what you get is where the work is. So anyway, this was kind of so we did this kind of as a challenge problem. Right? So these two people wanted to prove their manhood, and these two people wanted to prove their womanhood. Okay, so those are 8 examples, okay, of discriminants from very small to interesting. So let me say a few things about the Gelfand-Kapranos-Zelevinsky book. What's the book about? Okay, what are the points of this book? So main points in the GKZ book. What are the main points? Well, the way I see it, there's sort of 4 main points. Okay? And let me summarize the main points. The first main point is that almost all the classical resultants and discriminants have the form delta A. Okay? So it's a very powerful formalism. So if you have some classical resultant or discriminant for, forms and various variables, then by picking the appropriate A, that will give you, the discriminant or resultant you're interested in. Now, I should say, in all fairness, Gelfand, Kapranos, and Zelevinsky, they collect in their book many, many formulas. So from classical to quite recent. So really what you want, hopefully, is sort of determinantal formula. So ideally, you would like to have this kind of a formula, and sometimes you have it, and sometimes you don't, So that's the first insight, that many, many classical resultants have this delta A formalism for some A. So it's a very, very powerful, You have the freedom to pick A. You can model many, many situations with this. That's the first insight. Now the second insight is that we want to find a formula for the degree and the Newton Polytope. So one thing they do in this book, they develop a beautiful combinatorial theory of so-called secondary polytopes. And the key insight is that the Newton Polytope of the discriminant, so really they want to understand the Newton Polytope of the discriminant. That's what they're interested in. And to get their hand on this, they argue that this Newton Polytope is a Minkowski summand, of a very beautiful combinatorial polytope called the secondary polytope. So the secondary polytope of our yellow configuration A is a big polytope whose vertices are in one-to-one correspondence with the regular triangulations of A. This is a very important object in toric geometry, and it was introduced for the first time in this book and for this purpose. So they said, really would like to have the Newton Polytope. We can't quite get it. We're going to get something bigger called the secondary polytope, and then we have a Minkowski summand relation, right? So in terms of normal fans, the normal fan of the secondary fan of the secondary polytope refines the normal fan of the discriminant. Okay, so that's the second key insight. Now, based on these considerations and some pretty hairy homological algebra, they derive a formula. They give a so-called alternating degree formula for the degree of A. So really you would like to know the degree of this discriminant, right? And they give a formula, but under a very special hypothesis. So in the special case, when the toric variety, associated toric variety, associated with the matrix XA, by which I mean the image of the monomial map given by the matrix. So it's the image in Pn minus 1 given by the columns. So the columns of A, they give us n monomials, homogeneous of the same degree. So we get a map into Pn minus 1. So that's a toric variety. It's the image of this monomial map when this is smooth. Okay. So if the toric variety is smooth, there's an alternating formula. Plus this, minus that, plus this, minus that is some number, and that number will be the degree. It's a Chern class calculation, basically. Okay. Now, the reason this works is another way. I could have defined the discriminant a little bit differently. So delta A really is the dual variety. It's the projectively dual variety of XA. Okay? It's another definition. So if you know about projective duality, the discriminant is the dual variety of the toric variety. And if you start with a smooth variety, then you can calculate the degree of the dual variety. There's a Chern class calculation, and they apply that, and they get a formula in terms of A. Okay? Now let me get critical. So I've been praising this book, but there's something bad about this. There are two hypotheses. One is that the variety has to be smooth. Now, in the examples that I gave you, right, in these examples, so P1 times P1 times P1, so in these examples that I gave you, the varieties are smooth. So that's okay, right? However, in practice, when you use these kind of methods to solve sort of computational algebraic geometry problems, in practice, these varieties are not smooth. If you have a sparse polynomial system problem, in generally, the discriminants, this is a great theory until you try to apply it to your problem. And then, and then your varieties, so the varieties that we see in statistics and so on, they tend to be not smooth. They have singularities, okay? Or I don't know about signal processing, but, in practice, varieties tend to be not smooth, including toric varieties. So that's too bad. Now the fourth point is these techniques that they develop. They have rather difficult techniques. I mean, the Riemann-Hilbert correspondence and perverse sheaves, and this is a hard book to read, okay? In spite of that, so these techniques are, let's say, they're advanced. Let's call them advanced. Advanced math, okay? So certainly beyond the level of these lectures, much more advanced. The techniques are advanced, but give little information. But give little information when the toric variety is not smooth. They give a little, they give some information, but not a lot. When the toric variety is not smooth, it's quite difficult, to calculate the dual variety when the variety is not smooth, or when the codimension of the discriminant is greater or equal to, right? We've seen an example. So, for instance, in the example of P1 times P2, in the Toblerone example, we had this case. It was not a hypersurface. So in those cases, you actually don't get very much information. Okay, so it's a great book, but I like to kind of advertise our paper, right? So that's why I'm here. Okay, so there's a new approach. Well, not just our paper. I want to sort of advertise, tropical methods, right? So new approach is the paper with Bekenstein and Feichtner that I showed you, and it basically redoes the theory in what I think is a much simpler way at the level of these lectures, drawing pictures and so on, from first principles. I mean, you don't need, Riemann-Hilbert correspondence and all this, let's say, advanced techniques. So essentially none of this is needed. And it's based on the following idea. It's based on the idea that we can tropicalize a certain morphism. We tropicalize a certain morphism. And this morphism is a beautiful map. It's called the Horn uniformization. The so-called Horn uniformization. So this is a parametric description of the discriminant. So I've given you two descriptions of the discriminant. I've given you a description of the discriminant as coefficients that make the variety singular. I've given the description as a dual variety. But there's actually a very nice, parametric description And that's due to Kapranos, so this is Kapranos horn uniformization. And it's the following. You start with the toric variety, and you multiply it. You take the Hadamard product with the kernel of A. Okay? Now that's a crazy formula. What does this mean? Okay? So these things, all of these things are projective varieties. Right? So what on earth does this mean? So these things are, whatever they are, both the left-hand side and the right-hand side is a projective variety in Pn minus 1. This is the thing we want. Okay? This is a toric variety. So that's a projective variety. The kernel of A, that's a linear space. Okay? That's a linear space in this projective space. And the product is simply the coordinate-wise product. So I take any vector here, any point here, and I take any point there. Okay? And I multiply coordinate by coordinate. Just coordinate-wise. Now, I could be unlucky. It could happen that these products are all 0. Right? It could happen that these two vectors have disjoint support, and in this product I get the 0 vector. Those I throw out. Right? So I take only the ones that give me a non-zero vector. That's a set. Okay, that's a subset here, and then I take this risky closure, okay, and then they equal. Okay, so that's Kapranos horn uniformization. So that was a very, very nice observation, but it wasn't so useful at the time. So that's in the book, but they didn't get a lot of mileage out of this because they didn't know about tropical geometry. Right? You do now, right? Now you see this formula, you know exactly what to do, right? You do the obvious. So all we did the obvious. So the obvious is to formulate the following theorem. You simply tropicalize this formula. So theorem says the tropical A discriminant the tropicalization of the A discriminant, so that's the tropical variety of A, is equal, well, you tropicalize this and you tropicalize that, and multiplication turns into addition. Right? Now, in this case, the morphism commutes with tropicalization. Right? In general, morphisms don't commute with tropicalization unless you have a multiplication, unless you have a monomial map. Right? So this is induced a morphism of tori. So in this case, unlike in yesterday's secant case, in this case, tropicalization does commute. So we simply tropicalize this now. So this is a toric variety, right? So what's the tropicalization of the toric variety? Classically, this is just the row space of the matrix A. Right? So this is, this toric variety becomes this classical linear space. This multiplication becomes plus, becomes Minkowski addition. Now the kernel of A, right? That's actually the hardest part. So that's just, the kernel of A, right? So that's the tropicalization, and this is all in tropical projective space. Okay? So the obvious tropicalization holds. Okay? Now, what is this one? Well, this is a tropical linear space, right? So this is a constant coefficient tropical linear space. So team matroid, right? So here we need, to calculate the matroid of A, and then we're ready to go, right? So we write this down, There was lecture 5, right? So in lecture 5, we learned how to write this down, right? We just add the Minkowski sum. Let's check that the dimensions are okay. So let's look at the dimensions modulo the all one vector. So let's check, just make a little argument. So A is a D by N matrix that has the all one vector, in its row space. So therefore, modulo the all one vector, this becomes there we need this all one vector business. So this becomes a D minus one dimensional classical linear space in, N minus 1 space. Now what about this tropicalization of the kernel of A? Well, the kernel of A, that's an N minus D dimensional space. Now in projective space, so it's an N minus D minus 1 dimensional projective space. but the dimension stays the same by the structure theorem, right? So therefore, this one and this one, so if they meet, if they're in general position, this adds up to n minus 2. So the expected dimension of this is exactly codimension 1. The expected dimension is n minus 2, and that's the reason why typically it's a hypersurface, right? Now it could happen in some special cases that, that it's not a hypersurface, and the Green Book gives little information, when that happens. But this is kind of a characterization. It happens, there's a rank deficiency if and only if, there's a collapse, dimension collapse in this sum. So that's a hypersurface. So, okay, so what good is this theorem? I mean, I like to use this to calculate the discriminant, to actually get the discriminant. So let's see what we can do with this. Okay, so this tropical variety, as I said, is a hypersurface. I'm going to go over by about 5 minutes, okay? Is a hypersurface if and only if the discriminant is a hypersurface. And in this case, the Newton Polytope of the discriminant is computed as follows. Okay, so I'm going to compute for you the Newton Polytope of the discriminant. I'm going to give you a formula for the Newton Polytope of the discriminant. Now, in one sentence. No hypotheses whatsoever. Any matrix A, no smoothness hypothesis. I'm going to give you, a formula. Okay, so here's what you do. To tell you this polytope, I'm going to tell you the vertex in some direction. So you give me a generic W. And so let's say, Hyungju gives me his favorite. So this is some Newton Polytope, some big unknown Newton Polytope. I'm going to tell it to you. So the way I'm going to tell it to you is you give me a linear functional, and I'm going to give you the vertex back at which this is maximized, or minimized. Okay? In other words, you give me a term order, and I give you the leading monomial back. And then you give me another term order, so we're going to play this game. So I'm going to give you this polytope by giving you the optimal vertex in any direction. If you ask me enough questions, you have the polytope. Okay? So for a generic W, I'm going to give you this vertex, and I'm going to give you the ith coordinate. So the exponent of xi in the monomial. In the leading monomial. So this is the leading monomial. And it's the exponent, so xi, the power of xi in the desired leading monomial is the following number, is the number of intersection points. Is the number of intersection points of this tropical hypersurface over there, right? So of this thing with the ray half ray W plus non-negative multiples of EI counted with multiplicities. That's it. That's the answer. Okay? That tells you any leading monomial of the discriminant. So again, what about, let me say a word about the multiplicities. So there are two multiplicities here. There's an extrinsic multiplicity and there's an intrinsic multiplicity. So the first thing you do is you calculate the right-hand side. It's purely elementary. Everything you need to know is on the blackboard, right? You look at the row space of A, then you calculate this tropical linear space. Team matroid helps you. You might need to look at flags and things, you know. So then you add these two things together and you get a tropical hypersurface. There it is. But you get more out of this. You also get multiplicities. So each maximal cone, just like in GFAN, comes with a positive multiplicity. So now Professor Ahn gives me W, his favorite term order. That's a point somewhere in the space. And then I attach the ith ray, EI, right? And since W is generic, this ray will meet this hypersurface in finitely many points. At each point, I have an intersection multiplicity. Well, it's a codimension 1 plane, rational, meeting with a rational line. So there's a determinant. There's a lattice index. That's the extrinsic multiplicity times the intrinsic multiplicity. They're all positive numbers. I add them up, and I get a positive number. I do this for every I, and I get the degree. So you only need one term order to get a degree for the A discriminant. So I've given you, on this blackboard, with no advanced math whatsoever, an explicit positive formula for the degree of any A discriminant. And positive formula means it's not alternating. It's a sum of positive terms, and there's no smoothness hypothesis. Okay? Let's see one example, then we're going to wrap up. So example, very simple example, just to kind of summarize. So how to compute the determinant of a symmetric 3 by 3 matrix. Okay, so how to determine the discriminant of a quadratic form. So I'm just going to use this to illustrate the method. Okay, so I'm going to show you now, using this methodology, how you calculate the determinant of a symmetric 3 by 3 matrix. There are 4 steps. Okay, so step 1. So step 1, well, first of all, you need to know what A are we talking about, right? So the A we're talking about is, so it's this A, right? So I have to start telling you what A is, right? So A is this. Okay, so we're going to be interested in calculating the discriminant of this A. 5, 6. Okay? So step 1. Well, there's a tiny trick, since we need to tropicalize the kernel. We're not tropicalizing the row space. We need to look at the dual. So now, step 1, we need team matroid. So team matroid, we need to say, consider the dual matroid, of this picture. So the dual matroid will be a rank n minus d matroid, or an n element set. Okay? So that's the matroid. So step 2, let's call that matroid M. Okay? So this dual matroid is M. Step 2, draw the tropicalization of this matroid. So that we learned in lecture 4, right? That's the tropicalization of this matroid. And, well, this matroid is actually self-dual, so it turns out, it's kind of a self-dual picture. So what happens is, it becomes a 1, 2, 4, 4, becomes 2, 1, 3, 6, 2, 3, 6, 1, 4, something like this. A 5 goes here. Okay, that's the dual picture. And so the corresponding tropical linear space. So what we need to do, remember what we need to do? We need to make a list of all the flats. So we have, the list of flats, and then we draw the graph. And this looks like this in this example. Like this, like this, like this. Like this, there are 9 flats. And this is simply the incident structure. 4, 5, 6. So these are the red in the red picture. So 4, 5, 6, 5, 2, 3, 6. Here's 6. 1, 3. 1 connects to 5. This connects to 4. Here we have 1, 2, 4. It's a non-planar graph. And then this 6 connects down there, which is 2. Okay? So this is a nice non-planar graph. So this is step 2. That's the tropical linear space. So this is the combinatorial data that we calculate here. There are 2 more steps to go. Now we calculate. Now we're going to add in the row space. Now this is really a 2-dimensional fan, right? So this represents a 2-dimensional fan in TP5. Okay, this is a bunch of 2-dimensional cones. Now we're going to add to this a 2-dimensional linear space, namely the row space of A. So step 3. Is to add the row space of A. Now, it's actually equivalent, or equivalently, project into the quotient. Let's do this in R6, maybe, or TP5 modulo the row space of A, which is an R3. Right? If you think about it for a moment, you have any subset of a high-dimensional space, and you want to add a linear space. You want to add a linear space. Well, it's the same thing as projecting modulo that linear space. Right? Adding a linear space, you have some set, right? Taking the Minkowski sum with the linear space gives you, a thing that has this linear space, and then it's the same as taking modulo, this projecting modulo, this linear space. So if you take this picture, modulo this linear space, what happens is that these guys, 4, 5, 6, 2, 3, 6, and 1, 2, 4, these vectors get mapped to the origin, and the image actually looks like this. Okay, so this is this picture. So we're getting this automatically. 2, 6, 1, 3, 5, 4. That's the image, So this is this one. So now we calculated this. That's exactly the same picture we had last night. And now we want to, calculate the determinant now. So now we note step 4, the polytope dual to this fan. Dual to this is the Newton Polytope of the discriminant. So this is the little game we're playing, right? You give me a weight vector. So your weight vector lands in one of these regions. Each of these regions is labeled by a monomial, which I recover. So the dual polytope will be the bipyramid. Bum, bum, bum. And then I get, x2, x4, x5, x3, x4 squared, and so on. I get the monomials back. And that gives me the Newton polytope. And then if I want the actual, discriminant, so then I might have to recover the coefficients using numerical linear algebra. Right? So now I know the polytope. I have a parametric representation. So I can plug in and I can solve for the coefficients. Okay, so sorry I went a little bit over time, but this shows you that kind of the how powerful and actually quite easy tropical thinking is. So here's a situation where we can use the tropical approach to give a very explicit description of all Newton polytopes of A discriminants, and we don't need any fancy machinery. And along the way we invented the theory of secondary polytopes, although I didn't tell you. Okay, thanks for your attention.